Hello everyone, myself Soumya BJ, Assistant Professor, Department of ECE, SJBIT. In this session, I am discussing about the Module 1 topic of microwave and antennas. The topic is about transmission lines. Let us first understand the general concepts of transmission lines. Whenever we tell any circuits or the networks, they are mainly made up of components that perform operations on the signals and some other components that only carry signals from one place to another with minimum distortion on the signals. In general, when I tell any circuit or any network, usually these are made up of the components which actually perform the operation on the signals, or they consist of the components which carry the signals. Just they will do the transfer of the signals from one place to another. They will not do any operation on the signals, and this transfer of the signals from one place to another will be done with minimum distortion on the signals. These components, which are actually responsible for the transmission of the signals, we call them as transmission lines. Means the components which are actually responsible to perform some operations on the signals, or which are responsible to carry the signals from one place to another, they are called as transmission lines. And these transmission lines, they come in various shapes and forms. Let us repeat. The transmission lines are the components that are responsible for the transmission of the signals, and these transmission lines consist of components which perform some type of operation on the signals, or they will just carry the signal from one place to another with minimum distortion on the signals. And these transmission lines, they come in various shapes and forms. Let us have a understanding with respect to the types of the transmission lines. The first one is actually representing the coaxial transmission line. In this coaxial transmission line, there will be two conductors. One is the inner conductor and is the outer conductor, separated by a dielectric substance. Next is the two-wire line transmission line. As you can see, there are two wires here. And next is the strip line. It means in this strip line, there will be a metal contact placed on the dielectric material, and its cross-sectional view is seen here. And one more is the microstrip line. In microstrip line, as you can see here, there may be strips that are present, many strips, more than one strips present on this dielectric material. And as you can see here, this is a cross-sectional view, and this can be called as a low dielectric medium, and this is the representation in which we are using a high dielectric medium. Since we are discussing with respect to the microwave signals, we need to understand the transmission lines corresponding to the microwave signals. So the transmission lines, as we know, they are used to transmit the energy from one point to another, and they can also be used as circuit elements like inductors, capacitors, resonant circuits, filters, also has measuring device at the high frequency. Basically, there are four types of transmission lines. One is a two-wire parallel transmission line, the coaxial line, the strip line, and the waveguide. When I tell microwave transmission line, basically there are four types of transmission lines. Okay, these four types of transmission lines are two-wire parallel transmission line, a coaxial line, a waveguide, a strip line, as well as in the strip line again we can have a microstrip line as well. Let us first understand the properties of the transmission line. Usually whenever I tell a transmission line, it will be having two conductors. As I mentioned in the coaxial, this is a coaxial cable actually we use in our home, in TV receivers and all. As you can see here in this coaxial cable, it has got two conductors. One is the inner conductor, another one is the outer conductor. These two conductors, we can tell that they are running in parallel. Okay, and this is one more example, a twin led transmission line here. And coming to the next property here, they can propagate a signal at any frequency. These transmission lines, they can carry the signal, they can guide the signal at any frequency, and whenever we go for the high frequency, it becomes a little bit lossy. And coming to the power handling capability, The transmission line can handle low as well as moderate amount of power. The transmission line can handle low as well as moderate amount of power, and these transmission lines, they will not be having any signal distortion unless there is some loss in the circuit, in the network, in the transmission line. They will not be having any signal distortion, and it may or may not be immune to the interference. Similarly, when the interference has been considered in the transmission, these transmission lines may be immune to the interference or they may not be immune to the interference. Coming to the last property, it does not have the EZ or HZ components of the fields. Whenever a transverse electromagnetic field is being considered, which is propagating in the Z direction, this transmission line, we can tell that it will not be having any electric field in the Z direction or the magnetic field in the Z direction. So, there will not be component with respect to the electric field and the magnetic field. Just let us have a repetition with respect to the properties again. The transmission line, it will be having, first and foremost thing is, it will be having two conductors running in parallel, and the second one is, it can propagate a signal at any frequency. At any frequency it can propagate a signal. And third property is, it becomes lossy at high frequency. And fourth is, it can handle low or moderate amount of the power. And fifth is, it does not have signal distortion unless there is some loss, and it may or may not be immune to the interference, and it does not have EZ or HZ components of the fields. And this is the coaxial cable again. Whatever, as you can see here, this is a cable that we use, actually a coaxial cable, and as you can see in this figure, the two wires, whatever two wires we use of this transmission line, they will be twisted. The reason for twisting this two wires is to reduce the interference as well as the radiation from discontinuities. The two wires of the transmission line, they will be twisted. The twisting is basically reduced, is being done in order to reduce the interference as well as radiation from the discontinuities. The twisting of the wires is being done to reduce the interference in order to reduce the interference as well as the radiation from the discontinuities. And coming to the transmission lines, which are actually represented on the printed circuit boards. As you can see here, in the printed circuit board, there is a dielectric material with epsilon r, and this is the material of the metal that has to be used here with width W. This is a microstrip one, and this is the strip line one, and this is the coplanar strips, because there are two strip lines here used parallelly, and coplanar waveguide one, which is called as CPW. And this slide actually depicts the microwave integrated circuit. As you can see, this is a microwave integrated circuit, and whatever we are seeing here, this is the microstrip line. This is the transmission line. We can tell that this is actually representing the microstrip line, and this is the transmission line, which is actually used to take this signal from this part and then transmit to the another part. Now let us have an understanding of the waveguides. As we know, waveguides is one type of transmission line. We have come across this waveguide in the laboratory. We have come across experiments on microwave test bench, and actually this microwave test bench is made up of the waveguides which actually guide the wave through heat. The waveguide is able to propagate the signal through its area or the aperture, we can tell, and this is how the waveguide looks like. And these are the examples in which actually we are using the waveguides here. Let us first have an understanding of the properties of the waveguides. The first property is it is having a single hollow metal pipe. The waveguide is having a single hollow metal pipe. As you can see, this is the single hollow metal pipe, and it can propagate a signal only at high frequency. The waveguide is a transmission line which is basically used at high frequency, that is in the microwave frequency range. So we tell that it is propagating the signal at high frequency. So we tell that the lambda is greater than lambda c, and the width must be at least 1/2 of the wavelength. Whatever width is been considered for the transmission of the signal with the width of the area, it must be at least 1/2 of the wavelength. And even in the lossless case, this waveguide will be having signal distortion, and it is immune to the interference. And one more important property is it can handle large amount of the power. It can handle large amount of power. And next is it has low loss compared with a regular transmission line. Whatever we have come across 2-way transmission line, coaxial, microslip-on, it has got low loss as either EZ or SZ components of the fields. This waveguide will be having EZ or SZ. As we discussed in the transmission line, it will not be having EZ or SZ component, but here it will be having EZ or SZ component of the field. Waveguide is also, as I told, it is one type of transmission line itself. Let us have just have a repetition with respect to the properties again. First property, it is having a single hollow metal pipe. Second one is it can propagate a signal only at high frequency, so lambda is greater than lambda c, and the width must be at least 1/2 of the wavelength. The width must be at least 1/2 of the wavelength, and it has signal distortion. Even in the lossless case, it has got signal distortion. And next is it is immune to the interference, and next is it can handle large amounts of power. It has low loss compared with the transmission line. It has low loss, and it has either EZ or HZ component of the fields. It has either EZ or HZ components of the fields. Next, we have an understanding of transmission line theory. Whenever I tell a lumped circuit, the lumped circuit is usually made up of what? Resistors, capacitors, and inductors. And in this case, usually we neglect the time delays, means the phase values, whatever changes is there, we neglect that. When I go for distributed circuit elements, there comes into picture the transmission lines. In the transmission lines, we need to account for propagation as well as time delays. The phase changes, whatever occur, they also has to be considered. So we need transmission line theory whenever the length of a line is significant compared with the wavelength. So the final conclusion is whenever the length of the line is significant compared with the wavelength, whenever the length of the line is significant, the length of the line is transmission line, is actually used for transmission of the signal, is more compared with the wavelength, we need to understand the transmission line theory. Now let us have an understanding of transmission line, analysis of transmission line by considering the circuit theory. Can we model the transverse electromagnetic wave supporting transmission lines per unit length by a circuit of lumped components? That is the question. Is it possible to model the transverse electromagnetic wave which is supported by transmission lines per unit length by a circuit of lumped components? By a circuit of lumped component, is it possible? Yeah, definitely it is possible. As you know, it is a spherical coordinate system in which we will be having x, y, and z, and if we assume the signal of propagation to be in the z direction, okay, and if we consider just a part of the transmission line, a small unit or length of the transmission line, and if I represent this as a delta z, and this transmission line has got a power provided which is being represented by the supply E of z, V of z comma t. Whenever the supply is provided, the current flows, which is represented as I of z comma t, and in the transmitting section we have a resistance, and the resistance is taken per unit length, so it is represented as R into delta z. With the resistance we have got the inductance, which is represented as L into delta s. With respect to this, a parallel combination of we have got the G into delta z and C into delta z, and at the output terminal, and the voltage changes with respect to this area as V of z plus delta z comma t, and current also changes as I of z plus delta z comma t. Now let us analyze this circuit theory. To devise a circuit model for the transmission line, basically we need to understand the physical mechanisms which are being involved. Let us know what are those mechanisms and what is the circuit model. If the conductor of the transmission line has finite conductivity, definitely there will be heat loss, and this is equivalent of what? A series resistor. So there is R into delta Z, and current flowing on both the conductors in opposite directions induces a magnetic flux density between the conductors, which can be modeled as an inductance along the line. Since the current is been flowing on both the conductors and they are flowing in opposite direction, this results in magnetic flux density between the conductors. And when I tell magnetic flux density, it is actually modeled as what? The inductance along the line. So in series with the resistance, we have got the inductance. Now, two conductors with finite surface areas and finite separation distance can naturally be modeled as a capacitor between the conductors. And whenever we are as we know, we are using two conductors, right, and these two conductors have got finite surface areas as well as they are having a finite separation distance. One is inner conductor and another one is outer conductor. Each is having a finite surface area as well as finite separation distance, and they can be naturally modeled as what? A capacitor between the conductors. So there is a capacitor C into delta Z. Now finally, the finite conductivity of the dielectric medium between the two conductors, that is the loss, would cause the current to leak through the medium and modeled as a conductance between the conductors. It means since there is a dielectric medium here between the two conductors, there is a dielectric medium and this is having finite conductivity. This will cause the current to leak through the media. Through this dielectric medium, the current will leak, and that is actually modeled as what? That is actually modeled as a conductance between the conductors. It is actually modeled as the conductance between the conductors, which is represented as G into delta Z. So in order to divide this, in order to get the circuit model, first we need to analyze the mechanisms that are being involved here, and finally we need to arrive at the circuit. And coming to the brief summary with respect to this circuit model, here since we are using the conductor, the conductor of this transmission line has got a finite conductivity, so there will be heat loss, and this heat loss is equivalent to what? The resistance which is connected here. Similarly, when I take the conductors, there are two conductors here and the current is being flowing on both the conductors in opposite directions, and this actually induces the magnetic flux density between the conductors. This is actually modeled as the inductance along the line. And similarly, these two conductors, whatever we are using here, they will be having finite surface area. There is a finite separation between the these two conductors. So, and this can be naturally modeled as a capacitor between the conductors. And since there is a dielectric medium here between the two conductors, there is a dielectric medium. The finite conductivity of the dielectric medium will cause the current to leak through the medium, and this can be modeled as the conductance between the conductors. This is how the circuit model with respect to the transmission line results. Let us now have an understanding with respect to the derivation of the transmission line equation. We need to know what is the governing equation for the voltage and current on the transmission line based on the circuit model of the line. This is the circuit model. Based on the circuit model, we need to derive what is the governing equation for the voltage and the current. For this, we will apply the voltage and current laws for the circuit. Basically, when we apply the KVL to the circuit, the V of Z plus delta Z comma T, that is the output, that is equal to V of Z comma T minus L into delta Z into dou by dou T of I of Z comma T minus R into delta Z into I of Z comma T. Similarly, when we apply the KCL, I of Z plus delta Z comma T is equal to I of Z comma T minus C into delta Z into dou by dou T of V of Z plus delta Z comma T minus G into delta Z into V of Z plus delta Z comma T. And this V of T comma Z or I of T comma Z, they are actually represented with respect to the real value as real of V of Z e power of j omega t and real of I of Z e power of j omega t. This is how the equations are being taken here. And finally, these KVL and KCL equations again can be realized as V of Z plus delta Z is equal to V of Z minus L into delta Z, and this can be written as dou by dou t of I of Z comma t can be written as j omega I of Z minus R into delta Z into I of Z. Similarly, KCL will be I of Z plus delta Z is equal to I of Z minus C into delta Z into j omega V of Z plus delta Z minus G delta Z into V of Z plus delta Z. Now rearranging these last two equations, and when we take the limit of the result in the following expressions, what actually we get is V of Z plus delta Z minus V of Z divided by delta Z. For delta Z equal to 0 can be written as d by dz of V of Z equal to minus L j omega I of Z minus R I of Z. This can be again written as d by dz of V of Z equal to minus Z into I of Z. This is nothing but L and R can be replaced with Z, minus Z into I of Z. Similarly, I of Z plus delta Z minus I of Z by delta Z. For delta Z equal to 0 equal to d by dz of I of Z equal to minus C j omega V of Z minus G V of Z. That is again equal to d by dz of I of Z equal to minus Y V of Z, where these Z and Y are the series impedance and parallel admittance per unit length on the circuit equivalent of the transmission line respectively. What is the Z and Y representing is, the Z is representing the series impedance per unit length and Y is representing the parallel admittance per unit length of the transmission line. And finally, the Z can be represented as R plus j omega L, this is the series impedance, and Y can be represented as G plus j omega C. That is, the series impedance Z is equal to the combination of R and L, and the parallel admittance Y is equal to combination of G and C. So finally, we got to know that d by dz of V of Z is equal to minus Z into I of Z. We need to do the we need to get the equation of the transmission line with the double differentiation. So differentiate this again, d square by dz square of V of Z is equal V of Z, it is equal to or we can just realize it with respect to taking the value on the left hand side as minus gamma square into V of Z is equal to 0. Again that can be rewritten as V of Z is equal to V plus e power of minus gamma Z plus V minus e power of gamma Z. One is the incident voltage, another one is the reflected voltage. Similarly, with respect to the current, this can be written as d by dz of I of Z is equal to minus Y V of Z, and that can be again done, double differentiation will be done for this, means we need to differentiate it again. So d square by dz square of I of Z minus gamma square I of Z is equal to 0, or I of Z is equal to I plus e power of minus gamma Z plus I minus e power of gamma Z, where the gamma is nothing but the propagation constant, that is equal to square root of zy, that is equal to square root of r plus j omega L into g plus j omega C. That is again equivalent to alpha plus j beta, attenuation constant and the phase constant. Alpha represents the attenuation constant, beta represents the phase constant. And if suppose in this expression r is equal to g is equal to 0, means it is a lossless line, the gamma is equal to square root of zy, that is equal to square root of minus omega square Lc, which can be again written as j omega root of Lc, that is nothing but j beta, because the beta value is square root of Lc, the phase constant value beta is nothing but square root of Lc. So the final expressions of the transmission line is V of Z is equal to V plus e power of minus gamma Z plus V minus e power of gamma Z. I of Z is equal to I plus e power of minus gamma Z plus I minus e power of gamma Z. Here the gamma is nothing but the propagation constant, that is equal to square root of zy, square root of r plus j omega L into g plus j omega C, that is equal to alpha plus j beta. Alpha is the attenuation constant, beta is the phase constant. If r is equal to g is equal to 0, suppose it is a lossless line, gamma is equal to square root of zy, that is nothing but square root of minus omega square Lc, that is j omega root Lc. Root Lc is nothing but the phase constant beta. Since the equations for the transmission line are to be expressed by using only a few number of unknowns. Here V plus and V minus if we consider as two unknowns, again in the current equation we have got two unknowns, that is I plus and I minus. Let us express this I plus and I minus also in terms of V plus and V minus, means the current equation also in terms of incident voltage and reflected voltage. As we know, first we start with the TOHL, that is equal to V minus divided by V plus, the incident voltage divided, the reflected voltage divided by the incident voltage. This is the expression for this. So, d by dz of V of z is, as we know, it is equal to minus z into I of z. In this case, d by dz of V of z is equal to, in the place of this I of z, we will do the substitution of this I plus e power of minus gamma z plus I minus e power of minus gamma z. Okay, that is nothing but minus z into I of z. Okay, and finally, we get the expression of gamma, as we know the gamma as equivalent to square root of zy. Here in the place of this, we can just replace the value by gamma by z, and this as minus gamma by z. And again, if I just segregate the value, this can be written as square root of z by y, and here also square root of z by y, because this characteristic impedance zc is nothing but square root of z by y. So, I of z will be equal to 1 by zc v plus e power of minus gamma z minus 1 by zc v minus e power of gamma z. So, finally, we express the current also in terms of incident voltage and reflected voltage. This is the expression for the transmission line equation, particularly the current equation of the transmission line, and this is the voltage equation of the transmission line. So, in this session, we started with the discussion of the basics of the transmission line, what is transmission line, and what is transmission line made up of, what are the types of transmission line, and how can we model a transmission line, do the analysis of the transmission line via the circuit theory, how actually the circuit model results, what are the mechanisms that are involved in the transmission line per unit area, per unit length, and what are the governing equations for voltage and current in the transmission line. Thank you.